In today's lesson, we're going to continue playing with combinations, but instead of looking at how many groups of objects and things like that, we're going to be looking at how this applies to an algebraic context. This will be our introduction to the binomial theorem. But before we really get into the binomial theorem, let's talk about Pascal's triangle. Pascal's triangle has a row-by-row pattern. Begins like this. Where you have a 1, and then a 1, 1, and then a 1, 2, 1, and then 1, 3, 3, 1. All very interesting, all very interesting. Question is, how do you get one row from the row above it? Well, you might notice that this 2 is 1 plus 1. And this 3 is 1 plus 2. This 1 over here is 1 plus, well, nothing. So if I want to get whatever goes here, I'm going to say that's the sum of those two, and thus must be 4. If I want to get whatever goes here, I'm going to say it's the sum of these two, and must be 6. All these rows will start with a 1 and end with a 1. And in between, the way we get those numbers is by saying it's the sum of the numbers just above it. If we were to continue this, we could fill in another row. It starts with a 1. The next is 1 plus 4. And then it's 4 plus 6. And then it's 6 plus 4. Then it's 4 plus 1 again. And then it's just 1 plus nothing. Quick! Complete 2 more lines of this. I should space this out better. You complete 2 lines of this. I'll space this out better. And then the race will really be on. That's efficient. There. There's a slight chance I ask you to add one more row to it later. I don't even know. Decide how much room you want. I honestly can't remember if I asked you to do that. There are some interesting things about it. If you really look. One interesting thing, it's not really interesting, but the diagonal's always 1s. But the next diagonal just counts up. 1, 2, 3, 4, 5, 6, 7. There's also a nice symmetry where you cut this in half and left side mirrors the right side. And you got 1, 4, 6, 4, 1. Or 1, 5, 10, 10, 5, 1. Or 1, 7, 21, 35. 35, 21, 7, 1. So all those things, in my mind, are kind of interesting. Oops. Redo. The real key about this, though, is that it actually gives us combination values. For example, this row right here actually gives us all the options for to choose something. Where this is to choose 0, this is to choose 1, and this is to choose 2. Or this row right here gives us all the options for 5 choose R. Where we have 5 choose 0, and 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. So we can use this table or this triangle to get NCR values without actually having to use the calculator for it. So if you want 0 choose 0, it's a little weird, but we have to pretend that instead of counting the rows starting at 1, we're going to start at 0. So this is row 0, row 1, row 2, row 3, row 4, row 5, row 6, row 7. And when we start counting in, we're going to start at the number 0 as well. But 0 choose 0, it's right there. It's 1. The value of 2 choose 1. We went into that row, said there's 2 choose 0. There's 2 choose 1. There's 2 choose 2. Bam. What you really need to make sure you can get out of this is this connection between the elements of Pascal's triangle and the values of combinations. Probably could have written this before this video started, but writing it now. So starting the counting at 0, row 0, row 1, row 2, row 3. And then for the elements in that row, element 0, element 1, element 2, element 3, element 4, element 5, element 6, element 7. If we do our counting like that, then NCR is found at row N, position R. Don't turn this into a line for me. So, without a calculator, let's get the value of all of those. 5 choose 2. Here's row 5. There's position 0, position 1, position 2 is 10. You want 6, choose 3. Here's row 6, starting because here's row 0, 1, 2, 3, 4, 5, 6. And we want position 3. Here's position 0, position 1, position 2, position 3. So this is equal to 20. Quick, try the others, no time, while I erase all these circles I have drawn. Oh, I have to redo that 20. That's fine. 7, choose 5. 0, 1, 2, 3, 4, 5. And 7, choose 3. 0, 1, 2, 3. That's the general basis behind reading Pascal's triangle and how it gives us values of combinations. But let's actually apply this somewhere. And this has a chance to be nuts. Or just straight up mind-blowing. But let's multiply some of these. So we're going to expand and simplify. Well, first one's just a plus b to the 0. Anything to the 0 is just 1. And anything to the power of 1 is just itself. Just for fun, I'm going to say there's a 1 coefficient for those. Because why not? I'm a teacher, I can do what I want. At some point, you hopefully learned how to quickly expand a plus b squared. But if you didn't, you can do some scrap work up top somewhere. I don't know. A plus b squared is a plus b times a plus b. A squared plus ab plus ab plus b squared, if I'm using FOIL, which gives us that. So we've got 1 a squared plus 2 ab plus a single b squared. And similarly, we can get a plus b cubed that's just taking a plus b and multiplying it by a plus b squared. Which gives us stuff, again, if we use polynomial multiplication, that gives us a cubed and 2a squared b and ab squared. This gives us a squared b. This gives us 2ab squared, and that gives us b cubed, which all in all gives us this. And when I write that down here, that's a single a cubed. We'll have 3a squared b plus 3ab squared, and then a single b cubed. Is there a pattern? Spoiler alert, yes, there is. But what is it? See if you can straight up write whatever a plus b to the power of 4 is without actually going through all these steps up here. So none of this actual expansion simplification, just jump straight to the final answer. See if you can do it. Pause this video as long as you want. Sit on it for a day or two. Or watch the video and figure it out that way. But really see if you can get it. See if there's a way to go from one line to the next. If there's similarities between anything else we've done in that lesson and whatever you see in here. But just so you know, I'm about to do it. So if you're still trying to figure it out, really pause now until you're ready to see what it is. I'm just going to straight up write the answer now. You have a single a to the 4. And then you'll have 4a cubed b. If you want, you can say this power 1. Why not? You'll have 6a squared b squared. You'll have 4ab cubed. And you'll have a single b to the 4. How did I get this? Maybe how you got it, depending on whether you saw the pattern or not. There's a bunch of things coming together. For starters, let's check out the coefficients. This was 1. This was 1, 1. This was 1, 2, 1. 1, 3, 3, 1. Where have we seen those numbers before? Oh, that's right. Right up here. So the coefficients are coming from Pascal's triangle itself, or, as we know the connection to be, from the values of NCR. So these are the values of 0 choose R. These are the values of 1 choose R. These are the values of 2 choose R. So here we've got 4 choose 1, 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. So it's all those combination values that we're getting those from. Exponents-wise, the exponents of A go from 4 to 3 to 2 to 1 to, nothing. And similarly, the exponents on B go from nothing to 1 to 2 to 3 to 4. So one counts down, the other counts up. And if we can kind of detect that pattern, then we can easily even get something like this, a plus b to the power of 8. That would suck to do by hand. Like, it wouldn't be the worst thing in the world, but it wouldn't be the most enjoyable by any stretch of the imagination. But let's predict it. We know what the coefficients are going to be. Maybe. We've only got up to row 7 here. So I'm going to use row 7 to help tell me what row 8 is. Excuse me while I just place this here for a second. Yeah, that's exactly what I wanted to do. I'm just going to put that there. So I know that one of the coefficients will be 1, and the next will be 1 plus 7, so I'll have 8. And then I'll have 7 plus 21, And then I'll have 21 plus 35. Then I'll, why is that so spaced? Then I'll have 35 plus 35. And then 35 plus 21. And the symmetry of the pattern should just give us the rest. All right. So those are the values of A choose R. Right, this is A choose 0, A choose 1, A choose 2, A choose 3, A choose 4, A choose 5, A choose 6, A choose 7, and A choose 8. All those are there. Variables wise, well, when we had A plus B squared, it started with A squared. A plus B cubed started with A cubed. A plus B to the 4 started with A to the 4. A plus B to the 8 will start with A to the 8. And we'll have A to the 7, and A to the 6, and A to the 5, and A to the 4, A to the 3, A to the 2, A to the 1, and then A to the power of 0, which is the same as 1. And for B, it started with nothingness, and then climbed up to 1, to 2, to 3, so on and so forth. So there's no B's over here. Am I doing anything? The heck? Weird things have happened. Why didn't I erase that? Sorry, everyone. Oops, yeah. A squared, A to the 1. So there's no B's over here, but there is a B here, just a B to the 1. Here we have B squared, B cubed, B to the 4, B to the 5, B to the 6, B to the 7, and finally B to the 8. And then there's just addition right now between all of those because there's only addition that we saw. So that's all the terms of A plus B to the 8. Let's start formalizing what we're seeing here. So, if we're expanding A plus B to the n, some general expansion, some nth power of A plus B, what happens to all these things? What happens to the coefficients? Well, we notice that we got the coefficients from Pascal's triangle. We also know that Pascal's triangle is the values of NCR. So, we can say that. So that's how we get the coefficients. They follow the values of NCR. What happens to A? Well, we notice it starts at the highest possible exponent and then drops down, down, down until it reaches nothing. So it starts at the highest possible exponent, n, and then drops for each next term. For B, it starts at 0. But then it goes up by 1. For each term. When we put all that together, whew, this can be a doozy to look at initially. Here's that coefficient part. This is us saying that A is going to start at a high exponent and go down. This one says that B is going to start low coefficient go up. And that's for term K plus 1. Not term K, but term K plus 1. So if you actually want term 1, then we're talking about term 0 plus 1, so like k is 0, which means you're choosing n, choose 0, a to the n minus 0, b to the 0. Just making sure we're subbing things in right here. And so k goes from 0 to n, and thus when you expand things, there'll be n plus 1 terms. When you expand a plus b to the 1, you get 2 terms. When you expand a plus b to the 3, there are 4 terms. When you expand a plus b to the 8, there are 6, 7, 8, 9 terms. So one more than the exponent itself. And again, if you want term 5, k is 4. If you want term 20, k is 19. So let's look at some of these. First of all, how many terms are there in the expansion of this thing? Well, n is 18. Therefore, there'll be 19 terms. This next one, we're asked to expand and simplify. We're going to use, let's get rid of all this. We're going to use this formula over and over and over again. Oops. Let's erase it again. So we're going to use it for the first term, for the second term, for the third term, for the fourth term, for the fifth term, for the sixth term. It could take up some space. So 2x plus 1 to the power of 5. We're going to pretend that 2x is our a, that 1 is our b, 5 is our n, and do this one bit at a time. Our first term will be 5 choose 0 in terms of the initial coefficient. And then we'll have a to the power of 5, 1 to the power of 0. Just remembering that this one starts at the highest possible exponent, this one starts at the lowest possible exponent. The next term will involve 5 choose 1. And now, instead of 2x to the 5, we'll see that exponent drop. And instead of 1 to the 0, we'll see that exponent rise. Next one over. Now we're at 5 choose 2. 2x is now to the power of 3. 1 is to the power of 2. And we keep going with this. So 5 choose 3 is next. Oops. That should never have been. Sorry, everyone. That should have been multiplication all through there. 5 choose 3. 2x to the 2. That continues to drop. 1 to the power of 3. That continues to rise. Next term. 5 choose 4. 2x is now to the power of 1. 1 is now to the power of 4. And the last term, 5 choose 5. 2x is to the power of 0. 1 is to the power of 5. So that's what's involved in the whole initial expansion step. So just parsing out what all those terms actually are. Dang, right, smaller. Now we need to simplify, so we need to actually get values for all these things. 5 choose 0 is 1. 2x to the 5, well, 2 to the 5 is 32. X to the power of 5 is x, and then 1 to the 0 is 1. 5 choose 1 is 5. 2x to the power of 4. 16x to the 4. And 1 to the power of 1 is 1. 5 choose 2 is 10. If you take 2x to the power of 3, you got 8x cubed, and 1 to the power of 2 is 1. 5 choose 3 is 10. 2x to the power of 2 is 4x squared. 1 cubed is 1. And continues along, 5 choose 4 is 5. 2x to the 1 is, I don't need brackets there, what am I doing? 2x, and 1 to the power of 4 is 1. 5 choose 5 is 1. 2x to the 0 is 1. 1 to the power of 5 is 1. And then the final step for simplification is just finishing off each of those terms. So 1 times 32x to the 5 times 1 is just 32x to the 5. 5 times 16x to the 4 times 1 is just 80x to the 4. 10 times x to the 3 times 1 is 80x cubed. 10 times 4x squared times 1 is 40x squared. 5 times 2x times 1 is 10x, and then 1 times 1 times 1 is 1. You'll notice like this is a bit more spacey than we might tend to write polynomials, but just in terms of my step-by-step organization as I go from one line to the next, I like to keep things aligned, right? So here's my first term, here's my second term, here's my third term, here's my fourth term, my fifth term, my sixth term, just so that when I'm checking my work, it's a bit clearer for me to see. You don't have to do it that way, but that's what I do. I triple dare you to try this next one. It's got a power of 6, so it's a little bit more of a doozy, possibly. But I believe in you, and you should believe in yourselves, and believe in the dream. Feel free to, again, pause this video, because I'm going to be forging ahead. With this is my A value, this is my B value, and that's N. Boy. Six choose 0. Six choose 1. Six choose 2. Six choose 3. 3. 6 choose 4. Oops. 6 choose 5. And 6 choose 6. After I do this step, I like to just do a quick double check over, and I use in 3 steps. First, I check my NCR values, make sure I've got here 6 choose 0, then 1, then 2, then 3, then 4, then 5, then 6. So I do that double check. Then I check my A's and their exponents, so x squared to the 6, x squared to the 5, x squared to the 4, x squared to the 3, to the 2, to the 1, to the 0. And then the B values and their exponents. So 1 over x to the 0, 1 over x to the 1, 1 over x to the 2, to the 3, to the 4, to the 5, to the 6. just making sure that the patterns that I know that are supposed to be there are there. And then, once I've established that, once I've done that quick check, then I'll be satisfied with moving on to the next step. 6 choose 0 is 1, x squared to the 6, and 1 over x to the 0. 6 choose 1, x squared to the 5, 1 over x to the 1. 6 choose 2, x squared to the 4, and 1 over x to the 2. 6 choose 3, is 20. X squared to the 3 and 1 over x to the 3. 6 choose 4. X squared squared and 1 over x to the 4. 6 choose 5. And 6 choose 6. And then the final simplification step. Is that. Final example today, find the 9th term of this particular expansion. It's got a lot of terms, it's got 14 terms. I don't need to find all of them, I just need to find the 9th term. And going back all the way to here, if you want term 5, k is 4. If you want term 8, k is 7. K is always one less than whichever term number you're after. So if we want term 9, that's term 8 plus 1. And now we can use that formula. The formula that says tk plus 1 equals all the stuff it said. Because we have it in this form, something plus 1. K is clearly 8 now. And we can plug that in. N here is 13. This is B, this is A. So it'll be 13 choose 8. A is 3x to the power of n minus k, so 13 minus 8, times B. B is negative y squared. And to the power of k, so the power of 8. And then we can simplify this thing. You might need a calculator for 13 choose 8. And then 3x all to the power of 5. And negative y squared to the power of 8. And putting that all together, is that. Whew. What a doozy. Lots of practice work to do. If you find it intense, if you're just a little confused or anything, you have any questions at all, please do ask away, let me know. Contact me so that I can follow up with you. Like, give it a try, give it a go, give it a spin, give it a shot, give it a whirl, give it a stab, and see what happens. Believe in yourselves, believe in the dream. I will see you in the future. Peace.